So let us try this problem. So we have been given mole percent of CO2, and this is 1.5. Similarly, we have been given mole percent of O2, this is 18 mole percent, 18. Similarly, mole percent of argon, %80.5. Once I know the mole percent, we can calculate mole fraction. So mole fraction of CO2, and this is denoted by xCO2, and this is same as mole percent divided by 100, so 1.5 divided by 100. Similarly, we can calculate mole fraction of O2, that is xO2, and this is 18 by 100. Similarly, we can calculate mole fraction of argon, and this is x-argon, that is 80.5 divided by 100. So what we are doing, if mole percent is given, so I have a formula something of this kind: mole fraction of ith component is equals to mole percent of ith component and this divided by 100. This will give you mole fraction. Now let us say part A. Calculate the partial pressure of oxygen in a mixture where we have total pressure is 745 torr. So we have been given P total, that is 745 torr, and we know the formula, that is partial pressure of O2 is equals to total pressure times mole fraction of O2. So basically we are applying this kind of formula: partial pressure for ith component is equals to P total into mole fraction of ith component. And this formula if I apply for oxygen, so I will have PO2 is equals to P total into mole fraction of oxygen. Now you see, P total is 745 torr, so this is 745 multiplied by mole fraction of oxygen, and this is 1.5, so this is 18 by 100, that is 0.18, so this is 0.18. And if I calculate this value, 745 multiplied by 0.18, so this is 134.1 torr. So we can give the answer in torr because its initial it is given in torr. So around 131 torr. Now let us discuss B part. B part says if this initial atmosphere is held to be 121 liter. So volume is given second time. So B part, volume is 121 liter, and we have been given temperature 295 Kelvin, 295 Kelvin, and then we have to calculate how many moles of oxygen are needed. Of course, this time again we will assume the pressure required is same, 745 torr. So pressure is 745 torr, and we can convert this pressure in atmospheric pressure, 745 divided by 760 atmospheric pressure. Now if we apply PV is equals to nRT, This time P total is equals to Vn times n tot RT. So this times number of mole is total and pressure is total. Now pressure total is, we have to solve for n total, so n total will be P total into V divided by R into T. So we will have n total, this is equals to P total is 745 by 760, and this is atmospheric pressure, and V is 121 liter and R is 0.082 liter into atmospheric pressure, mole minus 1, Kelvin minus 1, so it will go on the top. And temperature we have, temperature is given 295 Kelvin. So let us say we will have atmospheric pressure goes, we will have liter goes, Kelvin goes, so we will have finally mole 745 into 121 divided by 760 into 0.082 and into 295, and this is mole. Now let us calculate 745 multiplied by 121 and this divided by 760 into 0.082 multiplied by 295. So this is 4.9 mole. So this is total mole. So total mole we'll have and we have to calculate mole of oxygen. You see the problem here. We have to calculate how many moles of oxygen are needed, and oxygen is only 18% of the total mole. So we can use this idea. So moles of oxygen is 18% of the total mole. So moles of oxygen, this is 4.9, this is 4.9 into 18%. So this is 4.9 into 18 and this divided by 100. So this is 0.882 mole. So we will have 0.882 mole. So moles of oxygen needed is, moles of oxygen, this is 0.882 moles. So what we have done in this problem, we have basically applied, if partial pressure is given, then we can calculate mole fraction, or if mole fraction is given, we can calculate partial pressure, and the formula will be partial pressure is equals to P total times mole fraction. So this is the formula we can apply to solve these kind of problems.